Do you believe the most powerful forces in the universe are not just explosions and black holes? What if I told you they are so extreme that they can warp space, freeze time, and even grind away the very foundations of life? From ancient signals stronger than a billion suns to invisible jets rushing at nearly the speed of light, this journey is not just about size, it is about facing the unthinkable. Welcome to the dark side of cosmic power, where there is something so powerful that for a brief moment, it shines brighter than everything else in the universe combined. These are gamma ray bursts. They are incredibly short flashes of gamma radiation, which is the highest energy form of light. Often coming from galaxies billions of light years away, for a fleeting instant, they outshine any star, galaxy, supernova, or any other object. So, what triggers a gamma ray burst? The most common type happens when a massive star, far larger than our Sun, runs out of fuel and collapses inward. But instead of quietly becoming a black hole, this death spray jets of energy from the star's poles at nearly the speed of light. If Earth happens to be in the path of one of these jets, we detect a gamma ray burst. There is another type that occurs when two neutron stars, the incredibly dense remains of past supernovae, collide. These are known as short gamma ray bursts because they last less than 2 seconds. Yet, in that blink of an eye, the explosion releases more energy than the Sun will radiate in its entire 10 billion year lifetime. What makes these bursts even more mysterious is that they were discovered by accident in the late 1960s. During the Cold War, the United States launched satellites to detect nuclear tests, but instead of bombs, they saw flashes coming from deep space, opening one of the greatest mysteries in the history of astronomy. Gamma ray bursts are not just powerful, they are potentially dangerous. If one occurred nearby and pointed directly at Earth, it could cause massive damage to our atmosphere, stripping away the ozone layer and allowing harmful solar radiation to reach the surface. Some scientists even suggest that a mass extinction on Earth 450 million years ago might have been linked to a gamma ray burst. However, do not worry too much, the probability of a direct hit is extremely low. Most of these bursts happen in distant galaxies. In fact, the most distant record comes from a galaxy over 13 billion light-years away, meaning it happened when the universe was just a few 100 million years old. The timescales are also fascinating. Most long bursts last only 20 to 30 seconds, but in that short time, they release more energy than all the stars in the observable universe combined. It is like lighting a match that shines brighter than a trillion suns. This is why experts race against time to study them. They tell us how black holes are born, how matter reacts under immense pressure, and even what the early universe looked like. We use space telescopes like NASA's Swift and Fermi to capture them the moment they happen. Because they are so fast, telescopes must pivot quickly and begin recording. Almost instantly. Once a burst is detected, telescopes around the world scramble to make further observations before it fades. Indeed, they decay quickly. After the initial flash, a glowing afterglow remains for days or weeks, helping scientists locate the host galaxy and trace the cause. Some are so bright they can be seen with the naked eye. In 2008, a burst from a galaxy 7.5 billion light-years away was visible from Earth without a telescope. That is halfway across the observable universe. Think about that, an explosion from the other side of the cosmos, bright enough to see without help. That is true power. Many questions remain. Why do some stars become gamma-ray bursts while others do not? Are there strange physical processes at work that we do not yet know? Some scientists even suggest using these bursts to test theories of space-time, as gamma rays might interact with the structure of the universe itself during their long journey. The universe is not always the cold, quiet place we imagine. Stars actually collide. Not just passing by or pulling at each other with gravity, but physically crashing into one another. When this happens, it results in massive explosions, the birth of strange new stars, intense radiation waves, and even black holes. Stellar collisions are extremely rare but incredibly powerful, ranking among the highest energy events in the universe. With so much space between stars, how do they collide? After all, the next nearest star is over 40 trillion kilometers away. But in the dense centers of star clusters or in the chaotic aftermath of galaxy mergers, stars are forced into crowded spaces where orbits are disrupted. Sometimes two stars get close enough to pull each other into a direct hit. The most extreme cases involve neutron stars. When two neutron stars orbit each other, they continuously lose energy through gravitational waves and spiral inward. The moment they collide is called a kilonova. It is not only incredibly bright but also synthesizes heavy elements like gold and platinum, scattering them into space to seed new worlds. A 2017 event allowed humanity to both hear and see such a collision for the first time. Gravitational wave detectors on Earth captured the ripples from two neutron stars crashing over 100 million light-years away, followed immediately by flashes seen by telescopes across all wavelengths. This confirmed the reality of stellar collisions and revealed the origin of the rarest elements in the universe. Not all collisions involve neutron stars. Ordinary stars can also collide and merge into a single, larger star. These new stars are often unusually bright and unstable, pulsating or rotating rapidly. Such events are thought to produce blue stragglers, stars that look younger than the surrounding population. A pair of stars was once predicted to merge within our lifetime, creating a visible red nova spectacle, and though the timeline was later corrected, the excitement showed how rare and shocking these events are. Collisions can also trigger supernovae. In some dense binary systems, one star siphons material from another. If the victim is a white dwarf, it may eventually reach a critical mass and explode. As a Type 1a supernova, shining bright enough to outshine an entire galaxy. And what if a black hole is involved? A black hole colliding with a neutron star or another black hole produces a powerful burst of gravitational waves and sometimes a gamma-ray flash. These events help scientists test general relativity under extreme conditions and understand how massive weights warp space itself. The aftermath of a collision varies. It might form a new massive star or a collapsed object like a black hole, or it might send shock waves through nearby gas clouds, triggering the birth of new stars or ejecting high-speed particles that leave glowing remnants for thousands of years. In busy areas like galactic centers, stellar collisions might not be so rare, influencing the long-term evolution of star clusters and galaxies. Even outside these dense zones, stars can meet in a slow-motion catastrophe given enough time. In about 4 billion years, our Milky Way will collide with the Andromeda Galaxy. Most stars will pass each other by, but a few will collide, filling the night sky with new light and cosmic wreckage. The power of a magnetar is almost incomparable in the universe, far stronger than any magnet, medical scanner, or even the Earth's magnetic field. A magnetar is a type of neutron star, but it is no ordinary one. Its magnetic field is so strong it could wipe your credit card from thousands of miles away. When a massive star dies in a supernova, its core collapses. If the conditions are just right, it forms a neutron star with a twisted, ultracharged magnetic field. This star is only about 20 kilometers in diameter but rotates at incredible speeds with a magnetic field strength a quadrillion times that of Earth. How strong is that? If you were only 1,000 kilometers away, the magnetic field would literally pull your atoms apart, stripping electrons away from their nuclei. It does not just warp space, it disrupts the basic structure of matter. Magnetars are not quiet, they are known for violent energy eruptions called starquakes. Just as the Earth has earthquakes. The crust of a magnetar, made of ultra-dense matter, can crack under the pull of its own magnetic field, releasing a burst of X-rays or gamma rays. Some of these flares are strong enough to affect satellites and communication systems on Earth. In 2004, an eruption from a magnetar 50,000 light-years away briefly compressed Earth's magnetic field. That single eruption carried more energy than the Sun radiates in over 100,000 years, yet the star itself is no larger than a city. Magnetars are born spinning very fast, but their intense magnetic fields slow them down over thousands of years. Because they spin and have such strong fields, they shoot beams of radiation from their poles. If these beams sweep across Earth, we detect them as pulses. Magnetars are also unique because their fields are so strong they change the physics around them. Near these extreme fields, the vacuum of space itself behaves strangely, causing light to bend in ways normal physics would not allow. This might be evidence of magnetars literally altering the structure of space. Out of thousands of known neutron stars, only a few dozen are magnetars, making every discovery precious. They help us understand how stars die and how matter behaves under pressures we cannot replicate on Earth. Magnetars may also be linked to another mystery, fast radio bursts. Some scientists believe these sudden, intense radio pulses come from magnetars, a theory strengthened in 2020 when a signal was traced to a magnetar within our own galaxy. A magnetar might even be a precursor to a black hole. If it accretes too much material, it will collapse again. Thus, they are not only powerful but potentially short-lived, like a cosmic time bomb waiting to go off. Stars do not always die quietly. Some end their lives as supernovae, but a hypernova is an even more extreme finale. If a regular supernova is like a gunshot in the universe, a hypernova is a massive bomb. It does not just leave behind glowing gas, it forges a black hole directly at its center. Hypernovae are triggered by the deaths of truly massive stars that burn through their fuel incredibly fast. While our Sun lives for 10 billion years, these giants live for only a few million before they begin to collapse. Once the core has no more fuel to burn, it cannot resist gravity. In a regular supernova, the core collapses into a neutron star, but in a hypernova, the collapse goes deeper. The core's mass is so great that even neutron degeneracy pressure cannot hold it up, and it is crushed into a black hole. At this point, the situation becomes even more complex. The core falls inward while the outer layers explode outward. But unlike most supernovae which explode in all directions, a hypernova often forms jets shooting out from its poles at nearly the speed of light. These jets carry hundreds of times more energy than a regular supernova and can punch through the star's outer shell and into space. These jets are powerful enough to trigger a gamma-ray burst. In fact, many long-duration gamma-ray bursts are thought to be the products of hypernovae. For a few seconds, the dying star's luminosity outshines the entire visible universe. In 1998, a famous hypernova event was linked to a powerful gamma-ray burst, providing the first direct connection between these lethal cosmic flashes and the death of massive stars. In the moment of the explosion, new elements are forged. The extreme heat and pressure create heavy elements like gold, platinum, and uranium, scattering them into the universe to become part of future stars, planets, and even life. Every piece of gold on Earth likely traces its origin back to an explosion like this. Why do some stars die as hypernovae while others end as ordinary supernovae? The key lies in spin and chemical composition. Massive stars with rapid rotation and low metal abundance are more likely to form powerful jets and head toward a hypernova. Scientists believe that in the early universe, when stars were purer and faster, hypernovae may have been much more common. Interestingly, these events also shape galaxies. They do not just light up space, they push it. The shock waves from a hypernova can compress nearby gas clouds, triggering a new round of star formation, or they can sweep gas completely out of a galaxy, effectively killing the birth of new stars. Such events rewrite the life history of galaxies on a massive scale. Despite their power, hypernovae remain rare, but each one leaves an echo in space-time: the birth of a black hole, the forging of the heaviest elements, and sometimes, the most blinding flashes of light ever seen. There are objects in the universe as bright as 1,000,000,000,000 suns, with light that can travel across billions of light years. This light, which began its journey before the Earth even formed, comes from quasars. At the center of every quasar lives a monster, a supermassive black hole. But black holes themselves do not emit light. So how is a quasar so bright? The answer lies in the accretion disk. Black holes with masses of millions or even billions of times that of the Sun pull in massive amounts of gas and dust from their host galaxies. Matter does not fall straight in, it swirls into a disk, heated to a brilliant glow by friction and gravity, outshining the entire galaxy. Some of this matter is twisted and funneled by intense magnetic fields, shooting out from the black hole's poles as jets at nearly the speed of light. Some quasars are so distant that their light takes over 13 billion years to reach us, meaning we are seeing an image of the universe when it was only a few 100 million years old. The scale of a quasar's luminous region is also mind-boggling. A region bright enough to overwhelm an entire galaxy may be no larger than our solar system, like a single flashlight outshining a city that never sleeps. A single quasar can release more energy in 1 second than the Sun radiates in its entire 10 billion year life, and it can stay active for millions of years. When astronomers first discovered quasars in the 1960s, they were confused. They looked like stars in telescopes but had strange spectra. Only later did we realize we were seeing the burning hearts of distant galaxies, lit up by hyperactive supermassive black holes. Quasars also blow powerful winds and jets that clear gas out of their galaxies, suppressing new star formation. In a sense, a quasar is both a creator and a destroyer. It lights up the universe while shutting down the star factories of its host. Ton 618 is one of the most powerful quasars known, with a central black hole mass of about 66 billion suns. Its light left that world over 10 billion years ago. If Ton 618 were placed at the center of the Milky Way, it would be bright enough to overwhelm our sky. Not all quasars are easily seen, some are hidden by gas and dust, requiring infrared and X-ray telescopes to glimpse. As technology advances, we find more of these hidden giants, suggesting they may be even more common than we thought. Quasars also help us study dark matter and dark energy because they are so bright and far away. When their light passes through the universe, it is bent by massive structures, allowing us to see the invisible mass of the cosmos. Eventually, a quasar will run out of fuel. Once the black hole has consumed all available matter nearby, the core falls silent, unless new gas flows into the galaxy, causing it to briefly revive like a zombie quasar. Not all stars just shine quietly, some roar into the universe like cosmic storms. Wolf-Rayet stars and supergiants are the short-lived, extreme-behaving celebrities of the stellar world, with luminosities far exceeding that of the Sun. They burn fast, die young, and violently change the environment around them. Wolf-Rayet stars are not typical stars, they are the exposed cores of massive stars that have stripped away their outer hydrogen layers. The remaining core is hot, unstable, and blows out intense stellar winds at speeds of over 2,000 kilometers per second, strong enough to blow away their own mass in a relatively short time. Their spectra reveal their internal organs, showing the ash of deep nuclear fusion like carbon and oxygen. These stars are ticking time bombs with lifespans of only a few 100,000 years, a mere blink compared to the billions of years the Sun will live. At the end of their lives, they often explode as supernovae or hypernovae, sometimes triggering gamma-ray bursts that spray lethal radiation into space. Compared to them, supergiants are in a class of their own. Take Eta Carinii, for example. In the 19th century, it underwent a giant eruption nearly as bright as a supernova but somehow survived. In just a few decades, it ejected mass exceeding that of the entire Sun, leaving behind a glowing shell known as the Homunculus Nebula as a monument to its rage. Its end could be a hypernova or a supernova, creating a black hole and shooting out jets that could affect nearby life. Another extreme example is VY Canis Majoris, with a diameter over 1,000 times that of the Sun. If placed in the center of our solar system, it would swallow Mercury, Venus, Earth, Mars, and even Jupiter. Being near a Wolf-Rayet or supergiant is dangerous. Their outer layers are constantly boiling, throwing mass in all directions and peeling away their own atmospheres in giant storms. These extreme stars are the recyclers of the universe. The carbon, oxygen, and iron they scatter when they die are the raw materials for planets, oceans, and life itself. Without them, the universe would be a poor and boring place. Many of these stars gather in stellar nurseries, such as the Tarantula Nebula in the Large Magellanic Cloud, where R13601 resides, one of the most massive stars known, with a mass over 200 times that of the Sun. It is essentially being peeled by its own radiation and will likely explode in the near future. Observing these objects is not easy, as many are hidden behind their own debris, but astronomers use telescopes like Hubble, Spitzer, and James Webb to peer through the dust and capture the details of their birth and death. If you pack the mass of the Sun into a space the size of Manhattan, you get a neutron star, one of the coolest and toughest ob. Fast, they can rotate hundreds of times per second. These are called pulsars. They shoot beams of radiation from their magnetic poles, acting like cosmic lighthouses. Their magnetic fields are trillions of times stronger than Earth's, and the most extreme ones are the magnetars we discussed earlier, capable of triggering powerful starquakes. The physics inside a neutron star is even stranger. The pressure at the center is so high that neutrons might break down into a quark soup, a state of matter so dense that current physics can hardly describe it. These stars are also fragile. If they accrete too much matter from a companion or merge with another neutron star, they cross the threshold and collapse further into a black hole. The boundary between a neutron star and a black hole is terrifyingly fine. Neutron stars also reveal how heavy elements are made. The merger of two neutron stars has been tracked across all wavelengths, confirming that gold and platinum are forged in these dead star crashes. Some neutron stars even fly through the galaxy at high speeds, kicked out by the explosion that birthed them. Imagine a stream of energy from a cosmic fire hose strong enough to destroy an entire planet, then point that hose directly at Earth. That is a blazar. It is a special type of quasar, already among the brightest and most energetic objects in the universe, but with the key difference that its energy jet is pointed almost exactly at us. Every blazar has a supermassive black hole at its heart, pulling in gas and dust that heats up and accelerates to nearly the speed of light. Usually, these jets shoot out sideways, and we see them in radio or X-rays, but if one points at Earth, it becomes a blazar. These jets are highly focused and directional, making blazars some of the brightest objects in the sky even from billions of light-years away. What makes them more intriguing is relativistic beaming. Because the jet is moving toward us at nearly the speed of light, the radiation is stacked and brightened in our direction like someone shining a powerful flashlight directly into your eyes. Blazars are not always loud, they can be quiet and then suddenly erupt with flares of gamma rays or X-rays that can change in brightness by more than 10 times in less than a day. Their light is often polarized, revealing magnetic fields that guide particles like a roller coaster track. A famous blazar, Markarian 421, is bright enough to be seen with optical telescopes from hundreds of millions of light-years away. In 2018, a blazar was identified as one of the first sources of high-energy neutrinos, ghost particles that pass through almost everything. Blazars are essentially natural particle accelerators, accelerating cosmic rays to energies far beyond what human colliders can achieve. By tracking their flares and jets, we are learning how black holes grow and how energy is transported on the largest scales. If there is an ultimate ceiling for energy intensity, it is the Planck energy. In daily life, you almost never hear of it because nothing on Earth comes close. According to the underlying rules of physics, there is an upper limit to the energy a single particle can carry. To understand it, we must combine the three great constants of nature, the speed of light, the Planck constant of quantum behavior, and the Newton gravitational constant. Together, they define the Planck energy. This is about 10 to the 19th power gigaelectronvolts, a 1 followed by 19 zeros. This is quadrile. At the scale of the Planck energy, the strength of gravity rivals other fundamental interactions. Quantum effects entangle with the structure of space-time, and the very concepts of distance and time may break down. If a particle were truly to reach this energy, it would behave more like a miniature black hole than a common particle. Thus, the Planck energy is viewed as the threshold to a theory of everything. Here, general relativity, which describes the macrocosm, meets quantum mechanics, which describes the microcosm, forcing us to seek a deeper unification. Some speculate that at this scale, space-time is not smooth and continuous but pixelated and granular, though we do not yet have the tools to see it clearly. While laboratories cannot produce Planck energy particles, some ultra-high energy cosmic rays in the natural laboratory of the universe may approach this range. Where they come from remains a mystery, whether from exploding stars, blazars, or even stranger sources. Some even suggest that events involving the Planck scale would immediately collapse into black holes, making them forever invisible to us. This implies that parts of reality may be unknowable in principle, not because we are not smart enough, but because the universe does not allow us to cross that line. Every second of every day, invisible power rains down from space. Most of it passes right through you without a trace. Extremely rarely, one of these strikes the Earth's atmosphere with the force of a fast-pitched ball, but it is not a baseball, it is a single atomic particle. These are ultra-high energy cosmic rays. Primarily protons or atomic nuclei traveling at nearly the speed of light. Ordinary cosmic rays come from the Sun or supernova remnants. But ultra-high energy ones are in a class of their own. A single particle carries staggering energy. The Oh My God particle, recorded in 1991, carried the energy of a well-hit ball in a single subatomic speck. Its speed was so close to the speed of light that if a beam of light chased it, it would take over 200,000 years for the light to gain a single second's lead. Its energy is millions of times higher than what the Large Hadron Collider can produce, and we still do not know what its accelerator is. These particles are so rare that only a few fall per square kilometer per century. To catch them, humanity built the Pierre Auger Observatory in Argentina, spreading hundreds of detectors across a vast landscape. When a cosmic ray hits the atmosphere, it triggers an air shower stretching for kilometers. By measuring the energy and shape of this shower, scientists can trace back the energy of the original particle. Yet, where they come from remains a puzzle. Is it supermassive black holes, merging galaxies, blazar jets, or even stranger remnants of the ancient universe? Charged particles are tossed back and forth by cosmic magnetic fields, making their paths untraceable by the time they reach Earth, like a bullet that has ricocheted off 1,000 walls. Theoretically, these rays should be limited by interactions with the cosmic microwave background, yet we still detect particles that seem to break this line. Either our understanding of the rules is wrong, or the universe is performing new physics, making these rays a key to the hidden cosmos. The universe is expanding, and galaxies are moving away from each other like dots on an inflating balloon. However, not all galaxies are just drifting with the flow, they seem to be pulled towards something invisible and massive. Astronomers call this the Great Attractor. In the 1980s, scientists measuring the speeds of nearby galaxies expected to see a uniform expansion, but instead found our Milky Way and thousands of other galaxies rushing at about 600 kilometers per second toward a specific direction. This region lies behind the dense disk of our own galaxy, hidden in a zone of avoidance where dust and starlight are hard to penetrate. Using X-ray and infrared observations, the veil was gradually lifted, revealing a massive concentration of galaxies called the Norma cluster. This is part of an even larger structure, the Laniakea supercluster, which spans hundreds of millions of light-years. Yet, even this cannot explain all the pull. We later realized that the Great Attractor itself is being pulled toward the even more distant and massive Shapley supercluster. It is as if the Great Attractor is just an exit on a highway leading to an even farther destination. Is the Great Attractor dangerous? It will not cause us to crash into anything, the expansion of the universe is still winning. However, it shapes the overall flow of our local universe, showing that the cosmos is not smooth on a large scale but has deep undercurrents. Dark matter likely plays a major role here, possibly involving a new understanding of the geometry of space-time. A galaxy cluster is like a cosmic city containing hundreds to thousands of galaxies, superheated gas, and mysterious dark matter. Imagine two such cities crashing into each other in a slow-motion collision lasting millions of years. This is one of the most energetic events in the universe since the Big Bang. Individual stars rarely collide, but the superheated gas between them hits with immense force, creating shock waves of plasma at tens of millions of degrees that glow in X-rays. Take the bullet cluster as an example, a smaller cluster punched through a larger one like a bullet. While the hot gas was slowed down by the collision, gravitational lensing shows that the majority of the mass the dark matter passed right through without stopping. This is one of the strongest pieces of evidence that dark matter exists and does not interact like normal matter. These mergers are not one-time events. The clusters pass through, are pulled back by gravity, and collide again until they settle into a larger cluster. This process releases massive shock waves and radio remnants at the edges, where some galaxies are stripped of gas and die, while others are compressed into bursts of star formation. Theoretically, these giant mergers also produce very low-frequency gravitational waves, though current detectors cannot yet hear them. Imagine two giants made entirely of gravity swirling around each other, faster and faster, closer and closer, until they become one. They do not just shake their surroundings, they make space-time itself ripple. In 2015, the LIGO Observatory heard such a whisper for the first time, a gravitational wave signal from two black holes merging over 1 billion light-years away. This was the first time humanity observed a cosmic event through something other than light. We did not see it, we felt it. That merger converted the mass of about 3 suns directly into pure gravitational wave energy, and for a brief instant, its power exceeded the total light of every star in the observable universe combined. Since then, we have recorded dozens of such mergers, involving black holes of various masses, including the first clear discovery of an intermediate mass black hole. Every signal tests the limits of general relativity and helps us trace the family tree of black holes, how they form, whether through stellar collapse or by black holes consuming other black holes. A lopsided merger can even give the new black hole a kick, launching it out of the center of its galaxy. Next-generation missions like LISA will head into space to listen to the even lower frequency symphony of supermassive black hole mergers. Black holes allow nothing, not light, matter, or even time, to return. But what about the opposite? Is there a region where things only come out and nothing can enter? This is the concept of a white door, a mathematical mirror image of a black hole allowed by the equations of general relativity. Though we have never observed a white hole, some theories suggest they are connected to black holes through wormholes, where one end inhales and the other exhales into another part of the universe or even a different one. Other theories propose that black holes do not evaporate away but eventually rebound into white holes, spitting out all the information they once consumed, though this event might be too fast for us to witness. Some even suggest the Big Bang itself was a white hole event. For now, however, this remains in the realm of fascinating speculation. In 2007, scientists found a strange, brief radio pulse in old data from Australia. At first, people thought it was an equipment glitch, until similar signals kept appearing. They were named fast radio bursts. They last less than a blink of an eye but release as much energy as the sun does in a day. Because they are so fleeting, they are incredibly hard to track. With new telescopes like CHIME and FAST, we have now captured hundreds. A few repeaters have changed the game, showing that the source survives the explosion. In 2020, a magnetar in our own galaxy was caught producing a signal similar to a fast radio burst, providing a strong clue that magnetars are at least one source of these events. These bursts act as sonar pulses for the invisible universe. As they travel through space, they are sculpted by the matter they pass through, helping us map dark matter and the contents of the interstellar medium. Our Milky Way hides Sagittarius A star at its center, a black hole with the mass of 4 million suns, but that is a small one. Black holes like TUN 618 have masses exceeding 60 billion suns. In 2019, the Event Horizon Telescope gave us the first image of a black hole's shadow in the galaxy M87, turning the invisible into the observable. Supermassive black holes are not silent trash cans, they power quasars and blazars, their magnetic fields twisting matter into jets that stretch for hundreds of thousands of light years. They act as a galaxy's thermostat, regulating the birth of new stars. We have found a mysterious resonance between the mass of a black hole and its host galaxy, suggesting they evolved together. Near the event horizon, time slows down and light bends, effects that have been precisely measured in stars orbiting the center of our galaxy. How these giants began, whether from seed black holes or the direct collapse of massive gas clouds, remains one of the great mysteries of the early universe. The most magnificent engineering projects of the universe are the relativistic jets shooting from the poles of black holes. Gas in the accretion disk is heated to millions of degrees, and magnetic fields act like coiled springs to launch particles at nearly the speed of light. As they reach these speeds, relativity takes over, time slows down inside the jet, and its radiation is beamed forward with intense brightness. The jet from M87 extends over 5,000 light-years, and some systems reach millions of light-years, a scale of 10 Milky Ways, while remaining as straight as a laser. These jets heat or clear out gas in their path, shutting down star formation. While they are most famous in supermassive black holes, smaller black holes and even young stars have them, but the scale and energy of the giants are incomparable. About 13.8 billion years ago, there was no time, space, stars, or atoms. Then, in a single instant, everything happened. The universe expanded from an impossibly hot and dense point into the vast cosmos we see today. The Big Bang did not happen in a place, because there was no place before it. It happened everywhere at once, creating space and time as it went. In the first fraction of a second, the universe underwent inflation, expanding faster than the speed of light. After several 100,000 years, the temperature dropped enough for atoms to form, the fog cleared, and light traveled freely for the first time. This baby picture of the light is the cosmic microwave background, which we can still see today. It carries tiny ripples that were the seeds of future galaxies. Why it happened is unknown. Some suggest a quantum fluctuation, others imagine we are a bubble in a multiverse, or that the universe goes through cycles of bangs and crunches. What we do know is that the expansion is accelerating, and distant galaxies will eventually fade from view, leaving the night sky increasingly empty. In the late 1990s, astronomers realized the universe is not slowing down but is being pushed apart faster and faster by something invisible called dark energy. It makes up about 70% of the universe, while visible matter is only 5%. The most common explanation is that dark energy is the energy of space itself. Even empty space has a tiny amount of pressure that pushes space-time apart. The more space there is, the more dark energy there is, and the stronger the push. If this push continues to strengthen, it could lead to a big rip, where galaxies, stars, and even atoms are torn apart. Upcoming space telescopes like the Nancy Grace Roman will track how the structure of the universe grows over time to see if and how dark energy evolves. The most powerful force in the universe may well be this invisible director. That is all for our journey through the universe's most extreme powers. I hope this knowledge brings you wonderful dreams and a beautiful day ahead. See you next time.